good morning, everybody. So last time we started discussing Gaussian mixture models. So the idea is to express a given data set, right, and to fit a PDF to a given data set. And so PDF consists of a linear sum of Gaussians. Think of them as a bunch of hills, right? So all the data must fit under those hills. Each hill is a Gaussian, so the final expression is a linear sum of Gaussians, in such a way that the total area under the curve is right under the summation is again 1. So each Gaussian, it's a multivariate Gaussian, can be expressed as this expression we have seen last time. So 2 pi power n by 2 times determinant of this covariance matrix power half times e power minus half times x minus mu transpose this covariance matrix inverse times x minus mu. So this is the multivariate Gaussian where x is in Rn, right? Mu is also in Rn, and epsilon is in Rn by n. It's a square matrix. So how do you fit this kind of data? So for that we invoke the idea of a likelihood function. So if you have we have a hill, right, and if I have a bunch of data, then how do you so this x1 and x2, right? What am I trying to maximize? I'm trying to maximize the product of the probability evaluated at x1 times the probability evaluated at x2. So that, in a more general sense, will give you something like this. So the likelihood is defined as it's a function of the entire data set D and all the parameters, this capital theta, which is given as the product that over the data set, that is j goes from 1 to capital N is the number of points, right? And the evaluation over the PDFs, such as alpha I, pi of xj at theta I. Okay, so this expression, you take product of this, you plug in xj for this expression, this is a p expression, and take a product of all this is what you want to maximize. But this is very hard because you need to differentiate this with respect to the parameters, theta I and alpha and all, which is very complicated. So we wanted to take a log of this and make it into a summation. So that's called log likelihood given by this expression, which is basically ln of this L. Okay, so we have seen all this last time. So now what we will do is, starting from the simplest case, right, let us try to figure out how to solve this problem, how to maximize this, right? So our problem is to maximize this log likelihood. So let's take the simplest case, case 1, where k equal to 1. Okay, so only one Gaussian and n equal to 1, that is 1D data. So it's like something like you have a single hill and you have a bunch of points and you need to fit the Gaussian to a single hill. Okay, all the data points are on the real line. I'm just drawing like as if it's a 2D thing just to convey the picture. Okay. So how do you do that? So P of x this time is 1 by root 2 pi sigma into e power minus x minus mu whole square by 2 sigma square. So this is the expression for a single Gaussian. So the log likelihood expression will be capital N L D will be nothing but sigma j equal to summation of data points ln of 1 by root 2 pi times sigma. So sigma is outside this root, okay? So times e power minus half x minus mu whole square by sigma square. Okay. So if you take a log of this whole thing, you get again sigma j equal to 1 to n minus, so 2 pi power minus half, right? So take that, you get minus half ln 2 pi. And then it is sigma power minus 1, so ln of that. So it is minus ln sigma. Then ln of this whole exponential, so that exponent comes down. X minus mu whole square by sigma square. So this is the whole log likelihood expression. Right now, so this is this capital L. So what we need to, this capital L is a function of the data, and the parameters are mu and sigma. So this capital theta, right, consists of only two parameters, mu and sigma. So how do you find what is mu and what is sigma? So this is what we need to find out, right? So let us do that simple differentiation. So how do you do that? You just do dou capital L by dou mu. Okay, so if you look at this whole expression, only the last expression is a function of mu, right? Others are, there's no mu in the other terms. So this should be equal to 0. So you get simply minus half times 2 times xj minus mu, the sigma over j equal to n. Okay, so this is equal to 0. So that simply gives you sigma xj j equal to 1 over n minus n mu, right, is equal to 0. So mu is equal to 1 by n times sigma xj, which is quite intuitive. So basically saying that, right, so mu is actually the average of all the data, which is very good, which is what we're expecting, so we got that. Now, if you look at the expression for sigma, so sigma shows up in both second and third term, not in the first term. So dou L by dou sigma is equal to 0. So that's equal to the second term. This is gone. There's no sigma here. The second term there is sigma. So that will be minus 1 by sigma minus half into x j minus mu whole square. So sigma power minus 2, right? So that will give you minus 2 by sigma cube. So that whole thing is equal to 0. So this 2 and 2 gets cancelled. So you basically, minus and minus becomes plus. So you basically get sigma square is equal to summation xj minus mu whole square. Okay, so there's a whole square by n. Okay, so what is the expression? This is just nothing but our variance of the data. So that way it is quite intuitive and it's giving you what you expect. So when you're trying to fit a Gaussian to a bunch of data, a single Gaussian, right? And so the mu of that Gaussian should be the average of the data, and the sigma of the Gaussian should be the standard deviation, or sigma square should be equal to standard deviation of the data, which is what you expect. And you see that this grand framework is giving you, in this special case, the kind of results that you expect. Okay, so now that is case one is fairly intuitive and simple. So that, but that gives an idea of how this whole framework works. Let's look at case two, which is slightly more complicated. K is still equal to 1, so that is only one Gaussian. And but n, let's make it a general. Okay, so some n dimension, some integer. So then things start getting more complicated. So in this case, the log likelihood will be something like minus half ln 2 pi power n by 2 times that covariance matrix. So the square root we have taken out. Okay, so sorry, this then there's no half here. Minus half um, x minus mu transpose epsilon inverse x minus mu. Right. So now this is expression. So we need to differentiate this capital L with respect to. So we need to find out what is mu and what is epsilon matrix. So you basically have to do del of L with respect to mu is equal to 0. That's one equation. And so del of L with respect to epsilon equal to 0, that's the second equation. So if you do the first one, so since there is no mu in the first term, so this whole thing goes to 0. So derivative of this whole expression, okay, with respect to mu, basically gives you, so this is equal to j equal to 1 to n sigma this epsilon power minus 1 times x minus mu. Okay, so this is like of the form x transpose a half. Okay, so if E is this, del of E with respect to x is equal to just x. Now we have seen this long ago, so the same thing applies here. So you just get so there's an offset minus mu term, but anyway, but this is follows the same logic as this. So you get this expression is equal to 0. Okay, since epsilon inverse is constant, you can take it out, and you get epsilon inverse j equal to 1 to n. Sorry, xj minus mu is equal to 0. So again, you get the same thing what we got before. That is, mu is equal to sigma xj by n. Okay, so that part is like just like before, but epsilon part is a bit complicated because to differentiate this cost function with respect to a matrix, again, this is because epsilon is not a vector; it's a matrix. So it's so this is slightly beyond the scope of this course. So I'll just give you the result, and epsilon turns out to be basically 1 by n sigma j equal to 1 by n x j minus mu times xj minus mu transpose. So you see that xj minus mu times xj minus mu transpose is a matrix. So this is an auto product, right? And therefore, so that's how you get this epsilon matrix. So this is a covariance matrix. So divide by n. So this is also quite intuitive. In fact, that gives an idea of how we got this epsilon in the exponent in the multivariate Gaussian. No, the third one is the one which is most general and which is slightly more complicated. But with this background, we should be able to understand how the third expression, works out. Case 3, where k is greater than 1 and n is also again. So both are just general integers. Right now, how does it work? So again, this time the log likelihood, which is that is given as sigma j equal to 1 to n ln of this whole expression alpha I, sorry, ln of sigma. So I goes from 1 to k alpha I pi x for theta I. Okay, so where pi is the multivariate Gaussian, theta is its mu and epsilon matrices. So to understand this, what we will do here, so I'll just give you the results of this. But to understand this, I want to make an analogy with the fuzzy logic or fuzzy clustering algorithm, because there are some resemblances between fuzzy clustering and this expectation maximization algorithm. So for that, I'll quickly show the expression for fuzzy logic, and then I'll introduce the expressions for this case, the most general case. Yeah, so in fuzzy logic, what have we done? So if you look at fuzzy clustering, so I'll just say there is an analogy with fuzzy clustering. So we had two expressions. One is finding the weights, other is finding the mean values or xi bars. So this is what we have done in fuzzy clustering. How do we find the weights? So assume let p equal to 2, because there is this factor which parameter which controls the level of fuzziness, right? So I'll take p equal to, which is normally what we take. So if you do that in the numerator, you have 1 by distance square x j and xi bar by sigma q equal to 1 to k and 1 by distance square xj into xq bar. So this is what the weights are. And once you have the weights, the next mean vectors are simply given as wij square times xj by this is over the entire data set and divided by wij square j over. Okay, so this is the mean value. Now, one way to look at this is, so to extend this, okay, so 1 by distance square, this quantity increases, right, as you come closer and closer to some weight vector, right? An analogous expression that you can have here would be something like e power minus uh, xj minus xi bar whole square, okay, by 2 sigma square by sigma cube equal to 1 to k e power minus xj minus x cube bar squared by. So basically all that I'm saying is, instead of a 1 by distance square expression here, why not take a Gaussian expression? Because in both cases, right, as your data point comes closer to the centroid, the expression value goes up. Here it goes to infinity, of course, but then that will be taken care of by an infinity in the bottom, the denominator. So wij, when the data point comes very close to that given centroid, it will tend to 1. This is what happens in fuzzy clustering. We'll do the same thing, but with a Gaussian term, which is more easy to handle because it doesn't blow up. Okay, and similarly, this expression we can take it p equal to 2, we get this. If p equal to 1, we just simply get wij xj by wij. So you get that kind of expression, right? So in fuzzy clustering, we are only controlling. So in fuzzy clustering, the only thing we are finding is uh, we are finding xi bars and the weight values. In case of this expectation maximization by Gaussian mixture model, so what we call this is expectation maximization using a Gaussian mixture model. So that's what this whole algorithm is called. So here, in addition to just the, so there is something like the weights, but here all we are calculating not only the mu's, we are calculating this epsilon matrix, and we also have to calculate the alphas. We have three things to calculate. So how do we do that? So this expectation is nothing but our likelihood, our log likelihood. So the log likelihood maximization using GMM. So you're trying to fit a GMM, a Gaussian mixture model, to a data set. And how are you fitting it? By maximizing the log likelihood. That's what this whole algorithm is about. And once you fit that, each Gaussian represents a cluster. So this is the whole idea. So for this algorithm again has two parts. There's an expectation step, or simply called the E step, which is given as Wij is equal to alpha I P xj theta I. In the denominator, you have alpha q pq xj theta p. So you see that the expression is very similar to the previous fuzzy logic thing. So we said, this 1 by distance square we apply to a given centroid between data point and centroid, and divide that by somehow similar expressions for all the distances to all the other centroids. So instead of using, so the same thing I said, you can, instead of this 1 by distance square term, you can use a Gaussian. So now if you take one step further, instead of just a Gaussian, use the Gaussian with its corresponding weightage, because we are fitting a bunch of Gaussians to the data set, and each Gaussian comes with its own weightage. So this whole thing is sigma alpha I pi of x. Okay, right, and each of them. So this is uh, alpha 1 p1. So this is alpha 2 p2. Alpha I pi. So this whole thing is sum of Gaussians, and each Gaussian component is alpha I pi. Okay, and so weight is nothing but, I'm putting it loosely without using technical terms. To what extent a given data point belongs to the ith component of this k terms, or there are k components or k Gaussians. To what extent does a given data point belong to the kth component? That's what this WI represents. And that's in the earlier fuzzy clustering case, what does it represent? W represents to what extent a given data point belongs to a given fuzzy cluster. So here it's a similar idea. To what extent a given data point belongs to a given Gaussian component. And each of these component has its own weightage, because some Gaussians are big, some are small. Okay, so that is the intuitive meaning of this weight matrix. Now, once you have the weight matrix, in case of fuzzy clustering, we went ahead and calculated the mean vectors, the x bars, right, or xi bars. So similarly, in this case, we not only have the mu's, xi bar in this case notation is mu. We not only have mu, You have to calculate the epsilon matrix and the alphas, the coefficients. How do we do that? So for that, we have to first define something called Ni. So Ni is like similar to this. So the mass of a given cluster in fuzzy clustering, that is the number of points in a given cluster that in fuzzy clustering. Uh, so here that is given by Wij. J goes from 1 to n data points. This expression, if you remember, in case of fuzzy clustering, it is the number of data points in a given cluster or the mass of that given cluster. Here also it's the same thing, number of data points in a given cluster. So given this Ni, once you calculate Ni, in terms of this Ni, you can calculate other expressions. Given Ni, alpha I is also something like a relative mass of a given Gaussian, right? In the whole summation of Gaussian. That is, what is the mass of the ith hill, right? If you look at the entire set of hills, what's the relative mass of the ith hill? That is what alpha is. So that is simply given by Ni by capital N. So capital N is the total number of points, and Ni is something like number of points belonging to the ith hill. So that ratio is alpha. So given that the mu, so I'll call this the mu of the ith Gaussian, and this is mu nu. So this is also alpha nu is given by 1 by Ni times sigma Wij xj. J is equal to 1 to n. Okay, so this is similar to what we did in the fuzzy clustering case. It's just the average of all data points weighted by W's, because W gives you to what extent the data point belongs to the ith cluster. So here it's very similar idea. And the epsilon matrix, epsilon mu, right, for the ith Gaussian is very similar to what we did in this previous case, the case 2. Okay, so because in the case 2 we had only one Gaussian, so we divided that covariance matrix by n, which is the number of total number of data points. In this case, there are k Gaussians, so the epsilon I for the ith Gaussian is simply given by 1 over Ni times sigma Wij. J minus xi bar times j minus xi bar, sorry, transpose. Okay, so this is a covariance matrix, but for only the ith component. So j goes from 1 to n. Okay, so that's all. So earlier we had, in the case of fuzzy clustering, we had we were updating only the xi bars and whs. In this case, first you calculate whs. Using that, you first have this expression called Ni, which gives you the mass of the ith Gaussian component. Using that, we can calculate the alphas, the fractions, right? That gives the relative mass of the ith Gaussian. And then using that, you can calculate using these weights, you can calculate the means, mu I is nu, right? And then epsilon I mu. So once you have all these terms, so the second iteration starts. So this updating all these parameters is called the maximization step. The first thing is expectation step. Second one is maximization step, also called M step. Okay, so first you calculate the weights, the expectation step. In the maximization step, you calculate the Ni's and alphas and mu's and epsilons. Once you have this, you go back to the first thing, because once these are the parameters of the Gaussians, right? The PDF. So once you update all these parameters, you go back and calculate the weights again. Okay, you have the new set of weights. Then using the weights again, you calculate this. They keep on iterating from here to here and here back to here until the weights don't change any further. Right. So that if you do that, then you will get something like this. Okay. So you have this data set. So you start from some initial Gaussians. Here it has only two Gaussian components. Both are two-dimensional Gaussians. Right. You can see that this Gaussian is probably slightly has higher alpha than this Gaussian because it has slightly bigger area. Right. So we will actually look at some numerical examples. Sandeep will show a program to simulate this and show this. Right. I think that completes our discussion of expectation maximization by Gaussian mixture models. This is one kind of, so we said that there are this whole density based clustering methods. So here there are two kinds. Model based. So that is you calculate the density using a model, or you model the underlying density, which means you model the underlying density. That means you calculate PDF. Okay, the example of that is this expectation maximization by Gaussian mixture model. So that's what you have done so far. You have some data, you model the underlying PDF of the data, and once you have the PDF, each of the Gaussian components of that PDF gives you one cluster. So that is one approach. The other approach is obviously model free. Right? I won't calculate any underlying PDF, I won't calculate any mathematical expression. So directly estimate, so numerically estimate density. So now what does that mean? How do you estimate density without using any PDF? What is density? Can somebody answer that? What is, so because this is not, density is mass by volume in physics, but in this case, when you have a bunch of data, right, what do you define as? So you see that here there are, so if I look at this region, if I divide the whole thing into squares, into boxes, right, how do I define the density of points in each of these boxes?
Number of points by the area of the box, or
Very good.
number of points alone will just work.
Yeah, so number of points by the area of the box. I mean, boxes could be of same area, but so number of points by area of the box. So that gives a numerical estimate of density. So by that you can say that this box is high density, this is low density, zero density, and so on and so forth. So this gives us one more approach to calculating clustering, performing clustering. So what we will do, we'll introduce a new algorithm called DB scan. Okay, it says a big abbreviation. I don't remember right now. I'll have to look it up. So in DB scan again, we divide the space not into boxes. See, because if my data points are only present in some small part of space, right, and if I have to divide the entire grid up, the entire space into small grids and calculate density, that can be numerically very expensive. So I don't want to do that because my data is only present in this part of space. Why should I grid up the entire space? Entire space means what? You can't obviously go up to infinity, right? You have to define some huge box and grid up the whole thing, and gridding it up is even more expensive and complicated if you are looking at n dimensions. Okay, so this approach is fine for starters, but you need to be more efficient than smarter than this. and not try to calculate densities over the entire input space. We'll just only consider the part of the input space where there is some data. Okay, so in the neighborhood of regions where there is some data, you estimate density. Okay, so that means you're starting from the data points themselves, divide the space into small spheres, right, and then calculate the density of the points, the density of the data set in those spheres. Right? And so based on that, we can calculate clusters. So that's the intuitive idea behind this next algorithm called DB-scan. It's very powerful, right? In fact, if you look at some of the older clustering algorithms that we have visited so far, a lot of them have interesting theory, but when it comes to practical application, practical results, so they have so many handicaps, so many drawbacks. So we have seen that not only for k-means clustering, for hierarchical clustering also, right? Whether you use the min type or max type and linkage, different kinds of linkage you have, right? Each of them has some drawback or other. But whereas if you start clustering based on density in this kind of a model-free fashion, it's slightly computationally intensive, but you get excellent results with clustering. So let us see that in the next class. Right, we'll look at DB-scan, and the DB-scan will take us to a slightly different approach to clustering, which is graph-based clustering. So we'll next introduce graph-based clustering after DB-scan, and then combine ideas from DB-scan and graph-based clustering to come up with even more complicated and sophisticated algorithm for clustering. And with that, we are done with clustering. Okay, so we'll then go on to classifiers. So that's all for the day. And any questions? We'll do a simulation of this algorithm on Friday, right? But for now, are there any questions?
Is there any benefit to like picking density as uniform boxes? Like, why not some randomly like shaped divisions for each box?
So
It won't be a box then, but at least then you won't necessarily, like, I'm not sure whether this is actually the case, but maybe you won't, like, globularity of your data won't actually matter as much than if you just keep taking randomly shaped boxes and try and calculate them.
no, randomly shaped boxes means what? Some random polyhedron. What do
Yeah.
you mean by?
Yeah. I
But
mean,
why do
yeah,
you want
like,
to? That will increase the complexity, right?
I mean, but the complexity only increases once, like by 1/4 gets only while generating the boxes. No?
No, suppose I take some, I don't know, icosahedron or something like that. I don't
Yeah.
even know how it will work out in n dimensions. How will you find out if, or how will you calculate the number of points within that polyhedron? It's a
I mean,
hyperpolyhedron.
once,
It's very
yeah,
painful.
once you define the boundaries, after that, it's the same level of complexity. Like it's just an,
No,
just
but you
a,
can do with, so if you just calculate, so within a sphere means, I calculate the number of points within a certain radius around me. I am a data point. So first of all, dividing the entire input space into whatever shaped tiles is obviously very wasteful, because generally most input space will be empty. There will be data only, at some sparse locations, right?
yeah.
So first of all, when you talk about density, there's also implicitly this notion of scale, which figures. Um, so we will have to worry about that. So to avoid all those problems, instead of dividing the whole input space into some standard size boxes, unless the boxes are of right size, we may not get even meaningful results. Because let's say the points are spaced out at a scale of kilometers, and you divide the input space into boxes of size meters, you will get most boxes will be empty and it will be totally meaningless result. You need
One
to.
question: how complex is defining like a random shape, as in, like not in a polygon, like not what is in multiple dimensions a polygon? I can't think of the word, but I'm saying a
Yeah.
figure with like curved surfaces and all of that, but of the same area. Like you pick one area and then you divide the entire shape into curved surfaces. I guess that should have
No, in
some sort
fact,
of, yeah.
that's an interesting question because I don't know of any tiling result other than a hypercube, which is very simple.
Yeah.
I don't know if there's any other shape which will let you tile any other regular shape, which will let you tile n-dimensional space.
Yeah. I mean, you'll have some like boundary condition where like you'll have to, I guess.
No, so the whole point is the whole approach of tiling. Yeah, so that's the difference here. There are two possible approaches. One is the tiling approach where you fill the entire space with your tiles. What I'm trying to say is it's unnecessary and it's wasteful. It's a wrong problem we're trying to show. It's a difficult problem. And even if you solve it with great difficulty, it's useless. There are much simpler ways to go about the problem, which is don't worry about tiling the entire space. Just see where the data points are in the space and only estimate density in that neighborhood, not everywhere.
Okay, so then no, but I wanted the entire premise of my question is: would using any regular shape give you any sort of benefit over just like picking cubes or some n dimension like hypercubes as your
any other shape you mean?
Yeah. Does that confer any benefit? Because I'm guessing you lose some sort of by calculating density in such a like regularly defined format. You lose some sort of information for sure. I'm not sure what you lose.
No, so the simplest would be a sphere because I'm just looking at the radius, points within my radius, easy to compute.
Yeah.
Why do you want to do something more complicated than?
Yeah, that's what I'm assuming. When you're calculating and wouldn't the easiest be like cubes because
I just apply Euclidean distance, not cube, sphere.
Okay, right. You're doing it only for the points around your data.
Yeah, that's my main point I'm trying to make. Right, don't tile the entire space, just work around the data points.
I'll try and properly find out. I'll probably mail it to you.
Okay, cool.
Yeah, thank you.
Thank you guys. See you tomorrow. Bye.
Yeah, thank you, sir. And sir, second quiz we will have it on 6th of April.
6th of April, isn't it too far? Fine, okay.
Yeah, because we have this week and next week, and after that we have a week of break.
Right. Yeah. And also we need to. I'm planning to have NSEM somewhere around end of April.
27th, would it be fine? 27th Tuesday. If it is a 1 hour exam, then we can fill in that slot. But if it is 2 hour, then we have to go with Friday or Saturday.
Yeah, I think it might be 2 hours. So let us look for some other day, Friday or Saturday. But I just want to tell people that I want to finish it off like late April, towards end of April, somewhere 27th and 30th, something like that.
Correct. Yeah, 30th is a Friday, and then first is the Saturday. It will be